Hello, I'll be presenting the latest results from the CUORE experiment. So to start, for those who are not familiar, the primary physics goal of the CUORE experiment is to search for neutrinoless double beta decay. The two neutrino double beta decay, shown by this diagram on the left, is a standard model process, but is a second order weak interaction, and so is very rare, making it only directly observable in a few nuclei for which the single beta decay is either suppressed or forbidden, meaning that the nucleus has no choice but to wait for the double beta decay if it wants to decay at all. Neutrinoless double beta decay, on the other hand, is a modification of this process, shown by the diagram in the middle, where instead of having two neutrinos in your final state, you just have the exchange of a virtual Majorana neutrino, and in the final state, you just have the daughter nucleus and the two electrons. Neutrinoless double beta decay is not in the standard model, and its discovery would demonstrate that lepton number is not a symmetry of nature, and that neutrinos are Majorana particles. This is currently the most practical way we have of addressing the question of whether neutrinos have a Majorana nature or not. And this is due to the fact that although the process is necessarily extremely rare, it does have the advantage that its experimental signature is very clean. Looking on the right, in the typical two neutrino double beta decay, the two neutrinos can carry away some amount of the energy of the decay. And so when a detector measures the energy of the two betas in the final state, you have this spectrum from 0 up to the full energy of the decay. On the other hand, in neutrinoless double beta decay, you have no neutrinos to carry away the decay energy. And so if you measure the energy of the two electrons, you just have this peak at the full energy of the decay. And so any experiment searching for the zero nu process is designed to be able to pick out this characteristic zero nu peak at the full decay energy from any possible surrounding backgrounds. Now, I mentioned that there are a number of isotopes for which we can use to search for neutrinoless double beta decay, and most of those isotopes are shown in this chart here, with their natural isotopic abundance on the x-axis and the Q value of the decay on the y-axis. On this chart, you can see that tellurium-130 stands out for its high natural abundance of 34%, as well as its Q value, which is relatively high at 2527 keV, putting it in a region with low beta gamma backgrounds. In particular, the high natural isotopic abundance means that we can use natural tellurium in experiments, saving on the cost of enrichment, which is actually one of the primary costs of any double beta decay experiment. In addition, as an element, tellurium can be incorporated into tellurium dioxide crystals, which can be reproducibly grown in very high quality, and which can also serve as a detector material. For this reason, tellurium-130 is the isotope of choice for CUORE, and CUORE itself is then located at the LNGS underground lab in Italy. Any rare event search needs to be placed in an underground lab so that the detector isn't overwhelmed by cosmic muons. And so LNGS in its facility provides a rock overburden that's the equivalent of 3,600 meters of water shielding. This reduces the muon flux by about 6 orders of magnitude to 3 times 10 to the minus 8 counts per second per square centimeter, which makes it a very manageable level. In addition, LNGS has low ambient gamma and neutron backgrounds as well, given by these numbers on the left here. CUORE itself stands for the Cryogenic Underground Observatory for Rare Events. The detector material consists of 988 high-purity natural tellurium dioxide crystals measuring 5 by 5 by 5 centimeters each, arranged into 19 towers with 13 floors, shown on the left here. This total array of crystals gets a total mass of 742 kilograms, and out of the 988 crystals that we put in, 984 of them are active and able to be read out, giving us a very high efficiency on the detector mass that we've deployed. All of these crystals are placed into the innermost chamber of a very large cryostat, the largest of its kind in the world. A diagram of this cryostat shown on the right here, and this cryostat has world-leading properties in both size and power. It cools about 15 tons of material to below 4 Kelvin and about 3 tons to below 50 millikelvin, including not only the tellurium dioxide crystals, but also the lead and copper shielding that we have around it. The custom dilution unit that we have for this fridge offers 4 microwatts of cooling power at the operating temperature of about 10 millikelvin. Now, why do we want to cool the crystals to such a low temperature? For this, CUORE operates based on the bolometric technique. And the basic idea here is that as materials get down to very low temperatures, even a small energy deposit results in a very large relative change in temperature. And so if we're able to precisely measure that change in temperature, we get a very precise estimate of the original energy deposit, giving us a very good energy resolution. In the case of CUORE, The detector absorbers are the tellurium dioxide crystals themselves, shown on the diagram on the top and also in this picture on the right. And each of the crystals is instrumented with a NTD germanium thermistor. NTD germanium thermistors have an exponential dependence of the resistance on temperature. And so if we current bias the NTDs, then after an energy deposit causes a spike in the temperature of the crystal, we get the spike in voltage that we read out as shown in the bottom left here. After this initial spike from the temperature rise, the crystal gradually releases the energy back into the surrounding environment, which is the thermal bath provided by the cryostat through a weak thermal coupling. And this gives us a decay back to the baseline in the bottom left here over the course of some seconds, giving us the characteristic response of our crystals to any particular event. From these pulses, then, we're able to estimate the energy of each of them and eventually construct a physics spectrum that we use for an analysis. The bolometric technique offers a number of advantages from the perspective of a double beta decay experiment. The sensitivity of any double beta decay search that is not background free is shown by this expression on the top here. And in particular on the right are the parameters most important for experimental design. First is the mass times time on the top, which is just your exposure. The more mass of your material you have, the more of a chance you have of having a neutrino's double beta decay to observe. And the longer you run it for, of course, the more of a chance as well. And for this, we've managed to achieve 2 years of uninterrupted data taking at this point with a very high stability of our cryogenic apparatus, allowing us to now have over 1 ton year of total exposure. On the bottom of that expression, you have the background index and the energy resolution of your detector, which is basically your ability to distinguish between a zero new candidate event and background events that occur around it. For this, the bolometric technique allows us to achieve very good energy resolution. And in our case, we've reached less than 8 kV full with half max Q beta beta through a combination of fine tuning our detector parameters to optimize signal to noise, as well as employing various active noise reduction techniques. And lastly, our background rates are in agreement with our expectations, made possible by our strict radio purity selection criteria, a low background assembly environment, and the various passive shieldings that we have in the cryostat to block any remaining external and cryostat radioactivity. This plot shows the rate at which CUORE has been taking data since it was first commissioned in the middle of 2017. You can see that boxed in green was our first data release corresponding to the first 2 months of data, after which we had some long period of cryogenic maintenance where we improved upon our infrastructure to improve its stability. Our second data release is boxed in orange, and you can see that since then we've been collecting data at an almost continuous rate with only brief pauses between datasets for calibration and for any routine maintenance that we have to do. Our most recent result then is this data highlighted in red, where we've unblinded 1,038 kilogram years of exposure. And you can see that since then, we've actually continued to take data at a similar rate, and we expect to continue taking data at this rate into the future as well. The summary of our analysis chain is shown here, showing how we go from this pulse and voltage space in the top left to finally an energy spectrum that we can perform a physics analysis on. Each of these pulses is passed through an optimum filter to optimize our signal to noise. It goes through thermal gain correction to account for any small differences in the thermal response of our detectors as the baseline of our cryostat drifts over time. Energy calibration, we deploy calibration sources outside the cryostat at the beginning and end of each dataset, which we then use to turn the amplitudes of these pulses into actual energies. After that, we apply coincidence and pulse shape discrimination cuts, and then a blinding procedure before any last data quality selections, and then finally the unblinding for our actual result. And I won't go into detail about all of the steps of this analysis chain, but I will discuss the coincidences and the pulse shape discrimination, which are 2 of the most significant cuts that we have to improve our data quality. So first, for coincidences, we take advantage of the fact that we have a source equals detector setup, where the source of our 0 new events, which is the tellurium 130, is incorporated into our detectors, which is the tellurium dioxide crystals. What this means is that we expect about 88% of our 0 new decay events will deposit the entirety of their energy into just one crystal, which is the crystal that they originated in. And what that means is that if you have more than one bolometer fire in a small time window, then it's pretty unlikely to be due to a 0 new event and is much more likely to be due to some other external radioactive contamination or a muon-induced event or some correlated detector noise. And so we assign a multiplicity in total energy to each of our events, and we select only the ones that don't have any other signals in coincidence, selecting only these multiplicity 1 events labeled on the bottom here. Shown on the right is an example visualization of one of our high multiplicity events, with each of the cubes representing one of our detectors in our array. And here you can see that highlighted in red is a bunch of cubes that had energy deposits. And in this case, they form a sort of line, meaning that this high multiplicity event was likely due to a muon passing through our detector. After coincidences, we apply a pulse shape discrimination technique based on principal component analysis to remove any anomalous pulses and non-physical events. The basic idea here is that for each channel in a dataset, we can treat the average pulse like it's a leading principal component and calculate a reconstruction error, where we try to reconstruct every event using just this leading principal component and see how good of a job we do. For events like the top right, using only one principal component, we do a very poor job of reconstructing that event. And that means this is almost certainly not a signal-like event. Whereas for events like the bottom right, where we do a very good job of reconstructing the pulse, it probably is a signal-like event. And so doing this, we can normalize the reconstruction errors versus energy to get the scatter plot that's shown on the bottom here. And from this, we can just apply a cut on this normalized reconstruction error. And in our case, the red band shows the events that we actually select. Here you can see a number of the natural radioactive peaks visible, and you can see most of them are selected by the PSD, and there's just this random scattering of events across the spectrum that end up being rejected. The effects of each of these cuts can be seen in the spectrum here. First is just the base cuts, where we remove any periods with excessive noise or any channels that failed processing or had poor performance, as well as any events that had multiple pulses in the time window. After that, we apply the anti-coincidence cuts, which is this process of selecting only the single hit events using a 40 kV energy threshold and 5 millisecond time window. And then lastly, we have this PSD cuts, which is the PCA-based method to cut any remaining events that have anomalous pulse shapes. Looking at the spectrum, you can see that in some of the natural radioactive peaks, the anti-coincidence and PSD cuts keep most of the events in those peaks, as we should expect, since these are mostly signal-like events that are depositing on one crystal. Whereas if you look at the continuum between them, you can see the anti-coincidence and PSD cuts significantly reduce their background. And in particular around Q beta beta, you can see how much they reduce the background levels in that area. Next, we obtain the detector response function for each of our channels by fitting the 2615 kV calibration peak using a 3 Gaussian response plus these various background components that are labeled here. This 3 Gaussian response function is an empirical response function that we have for each of the channels, and this allows us to obtain the energy resolution and the full width half max for each of them. The distribution of the full width half max for each of our channels in each of our datasets is shown in this distribution on the bottom here. And we apply a 19 kV full width half max cut for the zero new analysis, which trims this tail to the right while keeping the vast majority of our channels in this bulk of the distribution to the left. After this cut, we obtained a 7.78 kV full half max harmonic mean at the 2615 kV calibration line. We also scale this response to the various background peaks in physics data to account for any possible discrepancies in the response between calibration and physics. And we see that the response at Q beta beta in physics data is about the same as what we see in calibration. A summary of all of these numbers for the 1 ton year zero new analysis is shown in this table here. In particular, the total exposure of our isotope of interest, tellurium-130, is 288 kilogram years. And I'll also point out that the analysis efficiency of 92.4% is quite high and is notably an improvement upon our previous results, mostly coming from an improvement in the PSD efficiency. Our blinding procedure is a simple salting where we just move some fraction of events in the thallium-208 peak down to around Q beta beta and vice versa. This gives us a signal-like peak filled with signal-like events that we can tune our zero new analysis on. And then after finalizing all of our procedures, we simply reverse the salting and move the energy events back to their proper energies. The actual zero new fit is a Bayesian analysis based on Markov chain Monte Carlo implemented using the BAT software package. The results on the zero new decay rate are obtained using a flat prior on non-negative rates. And as input to the analysis, we have the energy resolution and bias scaling. We have the detector response function and the various efficiency numbers that I've discussed. As free parameters in the fit, we have, of course, the zero new decay rate, as well as a Cobalt 60 rate, since there's a Cobalt 60 sum peak in our region of interest near Q beta beta, as well as the background rate for each data set and a shared linear slope to the background. We also repeat the fit with additional nuisance parameters to account for our various systematic uncertainties, and we find that the systematics in total have a 0.8% effect on our limit and corresponding best fit value for the zero new decay rate, which ends up being pretty much negligible. The final result is shown here with the best fit drawn in red on the right, the fit without the zero new component in green, and the corresponding 90% limit drawn in blue. Our best fit value is non-zero, but very much compatible with zero. And the corresponding posterior PDF on the decay rate is shown on the bottom left here. From this, we can extract a 90% lower limit on the half-life of 2.2 times 10 to the 25 years. And we also extract a frequentist limit of 2.6 times 10 to the 25 years for comparison against experiments that only conduct a frequentist analysis. From these limits on the half-life, we're also able to convert this into a limit on the effective Majorana mass and beta-beta, assuming that the neutrinoless double beta decay is mediated by the exchange of a light Majorana neutrino. Using the current range of nuclear matrix element calculations, this corresponds to a limit of 90 to 305 millielectron volts, where this range on M beta-beta comes from the uncertainties in the current nuclear matrix element calculations. We can also calculate what our expected exclusion sensitivity was. And for this, we generate a bunch of toy experiments, assuming no zero no signal, where we just Poisson fluctuate the background events and cobalt-60 events using the actual rates that we obtained from data. And we then fit each of the toys using the same model that we had and extract a corresponding limit on the zero new decay rate. And the distribution of resulting limits is shown on the right here. And here you can see that our median expected limit was 2.8 times 10 to the 25 years, which is somewhat higher than our actual limit of 2.2 times 10 to the 25 years. But you can see that our actual limit of 2.2 is well within the bulk of expected possible outcomes, where in this case there was a 72% chance of obtaining a stronger limit than our actual results, meaning that there's nothing unusual with our result. We just slightly undershot our expected limit. And in that sense, we were somewhat unlucky. From our fits, we can also obtain an estimate of the background and the ROI. In our case, the alpha region background actually accounts for 90% of the background in the region of interest, meaning that most of our background is from degraded alpha interactions, consistent with the expectations of our background model. And this can be fed into our background model as well. And in fact, our background model over our entire energy spectrum does a very good job of reconstructing all of the major features that we see. Here, drawn in red is the reconstruction of our background model, and drawn in blue is the actual data using about 1/3 of the total exposure that we used for the zero new analysis. In our background model, we simulate 60 contaminants and muons through Giant for Monte Carlo, accounting for their geometrical distribution around our detector, as well as accounting for event multiplicity, and putting everything into a Bayesian fit to obtain the result that's shown here. And given the sophistication of our background model, we're able to use this to measure very precisely the 2 neutrino double beta decay rate of tellurium 130. Here you can see that the 2 new spectrum drawn in yellow overlaps heavily with our background in blue. And so with the precision of our background model, we're able to measure the 2 new rate of 7.71 times 10 to the 20 years, which is consistent with previous measurements, but now by far the most precise measurement of the half-life to date. With the statistical and systematic uncertainties shown on the top here. And this result now as well is published as the PRL reference shown on the left. So in summary, CUORE has now exceeded 1 ton year of total exposure and continues to stably collect data with an ultimate goal of reaching 3 ton years of exposure before Cupid commissioning begins. With an analysis of 1,038 kilogram years of data, we observed no evidence of zero new double beta decay of tellurium 130, and we have a corresponding limit on the half-life of 2.2 times 10 to the 25 years at the 90% level. This also represents the highest sensitivity search for a neutrinoless double beta decay of tellurium 130 to date, with a median exclusion sensitivity of 2.8 times 10 to the 25 years. And with this data, you can look forward to other analyses in the future as well. Thank you.